All right, we're going to talk about systems of inequalities in linear programming. So this is going to be working on graphing lines or curves, and then understanding if I'm going to use a solid line or a solid curve to graph those, or in which direction I'm going to shade. So we're just going to talk about linear items. Okay, so if I have less than or equal to, I'm going to shade below. If it's y is less than or y is less than or equal to, I'm going to shade below. If it's x, I'm going to shade to the left. Okay, if it's greater than or greater than or equal to, I'm going to shade above. If it's y is greater than or y is greater than or equal to, I'm going to shade above. If it's x is greater than, I'm going to shade to the right of that line. Okay. If I have strictly greater than or strictly less than, so if I have this side, I'm going to use a dashed line or a dashed curve depending on what I'm graphing. If I have equal to, I'm going to use a solid. So a lot of times I tell my students, see a line, draw a line, right? If you see that line, you're going to draw a solid line there. So the first thing we're going to look at is graphing. So I have y is less than 2/3 x minus 1. So I'm going to graph this just like I would a normal line, okay? So the first thing I'm going to do is I am going to plot my y-intercept. So I'm going to come up here at -1. I'm going to put a dot. Now, I need to find my second point. I'm going to use my slope. So the top number tells me up and down. The bottom number tells me to the right. So I'm going to go up 2, 1, 2, right 3. There's my second point. Now that I have my 2 points, I have to determine, do I use a solid line to connect those points or a dashed line? Well, I look here. Y is less than. I don't see a line here, so I'm going to use a dashed line. So there's my dashed line. I now have to decide, am I going to shade above or am I going to shade below? Okay, y is less than it says shade below. So there's my shaded region. Okay. Now what we're going to do is we're going to just add on. We're going to add on a second one. So this is a systems. So I have 2 of them here. I have systems now of inequalities. So I'm going to graph both. And I'll go ahead and use different colors so that way I can kind of distinguish those up there. So I'm going to use green for y is greater than or equal to 1/3 x minus 1. So I'm going to come up here, I'm going to graph this just like a line. So I'm going to go find my y-intercept, 1, 2, 3, 4. I'm going to put a point at my y-intercept. I'm going to use my slope. So it's -1/2. The negative goes to the top number, so it tells me down 1, right 2. There's my second point. And now I have to determine, do I use a solid line to connect those points or a dash? Well, it's strictly less than. So I'm going to use a dash line. Less than tells me shade below. So there's my shaded region. Okay. Now, I'm going to go ahead and graph y is greater than or equal to 1/3 x minus 1. So I'm going to put in my y-intercept at -1. I'm going to go up 1 over 3. Now, I have to determine solid line, dash line. Well, it's greater than or equal to, so it's solid. So there's my graph of that one. I'm greater than, so I'm going to shade above. So now, my region that I'm looking at is all of this where it's combined. Okay, well, all of it where it's got both colors in it. Okay, so that's my feasible region. All right, now, the last thing we're going to talk about is linear programming. Linear programming, typically what it'll have is it'll have a max-min function. So p of xy equals 3x minus 2y. That's my max-min function. And a lot of times we're going to try and find that value that maximizes that or minimizes it. This is very important when you're looking at like profit loss, that kind of stuff. You might have lots of different equations here, cost versus profit. So what we're going to look at is we're going to look at graphing all these constraints. Okay, so these are constraints hopefully it'll create a feasible region, so a region bound. So this did not have any bounds. Now, when we're looking at a max-min problem, what we're going to do is look at the vertices of our feasible region. Okay, the vertices is where our max or min is going to occur. So the first thing is I have to graph it. Okay, so y is greater than or equal to 0. Well, y greater than 0 puts me in the quadrant 1 and quadrant 2, right? So it takes the x-axis, puts everything above it. Okay, x is greater than or equal to 0, takes everything from the y-axis to the right of it, right? Those are x values greater. So right now I'm starting in quadrant 1. That's why I kind of drew my graph like this. I know I'm in quadrant 1. These two constraints are already drawn. Now, here's my next one. Well, I have x plus y is less than or equal to 5. Most of us don't like graphing in this form, so go ahead and convert it. So y is less than or equal to negative x plus 5. So I'm going to go ahead and graph that. So I'm going to go up 5, 1, 2, 3, 4, 5. I'm down 1 over 1, 1, 2, 3, 4, 5. So I know it's going to be here. I am using a solid line here, so y is less than or equal to. And I'm just going to put an arrow going that way to just indicate where I'm at. Okay? So now I know I'm in this triangle here. That's my feasible region. Okay? Now I have to graph this. So we want to convert this here. So what I'm going to do is I'm going to subtract off my 2x. So now I have, here I have negative 2x plus 4. I have to flip that around. So I'm going to go ahead and extend this out. Okay, so I'm going to make this y is greater than 2x minus 4. Okay. Okay. So I'm kind of coming up through here like this, and I'm greater than, so I'm going to be in this region right here. Now, I did hand draw this, so I am having a little bit of a problem finding this coordinate right here. I want to be precise on it, okay? So if I look at my graph, it kind of looks like 3, 3, but I notice that I have a little bit of error in there. So what I'm going to do is I'm going to treat these like lines. So I'm going to set them equal. So I have y equals, I have x equals. I actually could come right here and say, oh, look at this. My y's cancel out, so I end up with 3x equals 9 or x equals 3. So I know this coordinate here is 3. That's good. Now I need to take this, plug it back in. So if I plug it in here, I have 3 plus y equals 5 or y equals 2. I could check it on this one. That would give me 6. 6 minus what gives me 4 minus 2. So this is the coordinate 3, 2. Okay, now I need to find this coordinate, and here. Well, this one's nice and easy. It's 0, 0. Well, this one should be pretty easy too, because on the y-axis, that's 5. So this is 0, 5. Now, what about this one right here? So I need to solve this here where it crosses the x-axis. Well, that's going to actually be 2, 0. There's my 4 points on my feasible region. I'm now going to take every single one of these points and I'm going to plug it into this. Okay? So now what I'm going to do is I'm going to take P of x, y equals 3x minus 2y. I'm going to find P of 0, 0. Well, that one's really easy. It's just 0. There's my 0. So now I have P of 0, 5. P of 2, 0, and P of 3, 2. And this becomes 3 times 0 minus 2 times 5, which is negative 10. 3 times 2 minus 2 times 0 is 6. And this gives me 3 times 3 minus 2 times 2, which is 9 minus 4, which is 5. Okay? So this is my minimum value. This is my maximum value. All right? So we don't know exactly what this is trying to find. We just know that this is our min-max function. Our minimum value is when we have 0, 5. So this might be like x could be, hey, this is, production. This is how much it, hours, workers that you have to pay, something like that, or, and so we just don't know. A lot of times you're going to have to find these constraints, okay? So that's systems of linear inequalities and linear programming.